October 2025. The solar system is entering a narrow, unpredictable window, one that no predictive model fully anticipated. Over the past weeks, a wave of 17 newly detected small bodies has begun streaming inward from the outer regions, converging on a timeline that mirrors the approach of 3I Atlas toward its perihelion. 17 in just over a month. That figure alone breaks decades of statistical expectations. Historically, detection rates for comparable objects are measured in singles per quarter, not coordinated bursts. But this isn't just about numbers. Early observations reveal something stranger. Each object carries a spectral fingerprint rich in carbon dioxide, water vapor, and complex organics, but with thermal and rotational behaviors that refuse to fit standard comet physics. Their light curves rise and fall almost in unison. Their activity ramps up simultaneously, despite differences in size, spin, and trajectory. Infrared scans detect sharply defined internal temperature gradients, too orderly to be dismissed as random subsurface variations. And within the noise of the deep space network, analysts are now picking up faint but structured electromagnetic patterns repeating across multiple bodies. This is not the kind of clustering that orbital mechanics alone explains. It looks coordinated, synchronized, deliberate, and all of it builds toward a single gravitational and temporal hinge point, 3I Atlas passing behind the Sun at the end of October. No official agency has confirmed an artificial origin, but the scale of this anomaly has triggered one of the fastest coordinated responses in modern astronomical history. Supercomputers, interferometric arrays, amateur telescopes, and high-level briefings are converging on the same question. Why now, and why here? The pattern has started to form, and if the trajectory holds, we are looking at an event that could rewrite the physics of how objects move, cluster, and possibly communicate in space. This is where it begins. A sudden influx of 17 small bodies into the inner solar system in less than 6 weeks is not just statistically remarkable, it's historically unprecedented. Since systematic sky surveys began, the background arrival rate of new long-period or interstellar candidates has remained relatively stable, rarely exceeding 3 or 4 in any comparable time frame. The October surge doesn't fit that curve. These detections are concentrated into a sharply defined temporal envelope that began on September 8th and accelerated through mid-October. It is now converging on a narrow peak window just before 3I Atlas reaches its perihelion. What makes this more than a coincidence is how clean the temporal clustering is. Normally, comet arrivals are smeared across months, shaped by the uneven geometry of their orbits and our survey limitations. This time the curve is nearly vertical. 17 objects crossing heliocentric distances between 2.1 and 0.8 astronomical units within a 40-day stretch. Every detection plotted against time falls along a smooth logistic ramp, as if the arrivals are part of a time cascade rather than a random scattering of celestial debris. The timing doesn't just look unusual, it aligns. The burst overlaps perfectly with the period when 3I Atlas approaches its closest interaction zone with the Sun's magnetic and gravitational fields. This isn't a vague correlation. Simulations from multiple observatories show a less than 0.002% probability of such clustering happening by chance. It's a statistical fingerprint of coordination, though what kind remains unclear. Survey teams have already cross-checked their instrumentation for biases. No systematic errors, no shared blind spots, no data contamination that could explain the clustering. The detections have come from independent arrays, the Pan-STARRS network, ESA's FlyEye systems, ground-based interferometers, and a series of amateur telescope networks tracking faint inbound trajectories. Each object carries enough astrometric precision to confirm that their arrivals are real, not artifact. But what makes this window even more unsettling is that the detections were not evenly distributed. The first few appeared faint, almost deliberately concealed in the noise floor. Then, within days, the signal clarity spiked. By the 12th object, light curves were arriving with an identical early ramp-up signature, as if the inbound bodies were activating or shedding material at a predefined solar distance. It's the kind of synchronized threshold behavior typically seen in engineered systems, not in the chaotic dance of icy debris. Astrophysicists have floated several natural explanations. A shared origin event, perhaps a fragmentation in the Oort cloud centuries ago, could theoretically lead to loosely clustered arrivals. But the orbital element distribution doesn't match that story. These bodies are not fanning out along similar trajectories. Their inclinations, eccentricities, and longitudes are scattered in a way that should smear their arrival times, not sharpen them. Another idea: a large-scale galactic tidal perturbation, a distant gravitational wavefront nudging multiple Oort objects inward at once. But again, the coherence in arrival timing and activity ramp doesn't line up with any known perturbation model. Behind the scenes, a quiet debate is taking shape. Is this just an extreme, improbable clustering, or something that has been timed or even triggered to coincide with the 3i Atlas event? And if it is, what mechanism could exert such coordinated influence across objects separated by millions of kilometers? This burst window isn't just a statistical curiosity, it's the first clear sign that the anomaly surrounding 3i Atlas is not isolated. It's spreading, pulling other bodies into its gravitational and temporal narrative. And as more telescopes point upward, the patterns inside those trajectories are about to get even stranger. The first thing researchers did when the burst pattern emerged was simple: run the numbers. Historically, cometary discovery rates have followed a smooth and predictable distribution. Even when occasional clusters appeared, they never broke beyond 2 to 3 sigma from the expected mean. What's happening now around 3i Atlas doesn't just exceed those bounds, it crushes them. Statistically, this event lands far into the tail of the probability curve, well beyond what any natural model comfortably explains. Current datasets from the Minor Planet Center and multiple Sky Survey archives show that the average detection of new inbound long-period or interstellar objects in this heliocentric distance range is roughly 3 per quarter. A burst of 17 in 40 days represents a deviation equivalent to a 12.8 sigma event. In statistical language, that means a probability so low that it's effectively indistinguishable from zero. This isn't a random fluctuation, it's an anomaly. But the spike isn't just about how many objects appeared, it's also about how sharply their detections cluster around specific solar distances and epochs. Plotting arrival distances shows an unnaturally narrow spread between 2.1 and 0.8 astronomical units, too clean to reflect random gravitational slingshots. Their temporal curve is even tighter, a steep front edge, almost like the leading wave of a controlled sequence. In other words, the arrivals look timed. Teams at the European Southern Observatory, NASA's Planetary Defense Office, and Japan's Deep Sky Interferometry Network have been cross-validating the statistics to rule out coincidence or detection bias. No seasonal survey artifacts explain the spike, no known telescope configuration change aligns with it, and the fact that multiple networks, using different optics, algorithms and calibration systems, reported near-simultaneous detections removes the chance of systemic error. Whatever is happening, it is being seen by everyone. This level of temporal coherence has forced a re-evaluation of baseline models for inbound debris. If this were a simple chain reaction, for example a breakup event far out in the Oort cloud, we'd expect to see gradual dispersal over years, not synchronized arrivals over weeks. And gravitational focusing by the sun alone can't generate this kind of wave. The only comparable patterns in astrophysical records come not from comets, but from engineered constellations, the way Earth's own satellites occupy narrow time windows during coordinated launches. The spike also exhibits something subtler but equally revealing: the velocity distribution. Normally, long-period objects arrive with a broad range of approach velocities, shaped by random scattering and past gravitational nudges. This cohort is unnervingly tight. Most objects share approach velocities clustered around 33 km per second, plus or minus 2 km per second. Such uniformity suggests some form of shared modulation. No natural mechanism currently known, fragmentation, tidal shock, solar gravitational focusing, produces such consistent speed without a common origin point in space or time. Some observers have proposed that the objects may not be newly inbound at all, that they could have been encoding or holding patterns for years, activated only recently to cross heliocentric thresholds at the same moment. If true, it implies pre-positioning, something more often discussed in the context of spacecraft than natural bodies. Critics counter that the data may still reflect unknown clustering mechanisms in the Oort cloud. Perhaps we've underestimated how gravitational wavefronts, or even galactic tidal forces, can shape long-period comet dynamics. But even these critics admit that the clean timing, matched velocities, and near-zero probability curve are deeply uncomfortable fits for standard celestial mechanics. In private, some analysts have begun referring to the burst not as a cluster, but as a deployment. A provocative word chosen carefully, but one that fits the numbers. If that framing proves correct, then the spike isn't a fluke. It's a signal, a structured intentional release sequence aligned to a larger orbital event. The data are unambiguous. Something about the sky over the past 40 days has stopped following statistical rules. And as the telescopes shift from detection to analysis, attention turns to the next question. What exactly are these objects made of? The statistical spike forced scientists to look closer, but it's the spectral fingerprints that turned a data anomaly into a full-scale scientific crisis. When the first object in the burst crossed 1.9 astronomical units, observatories immediately began spectroscopic monitoring to classify its composition. At first glance, the data seemed routine. CO2 and water vapor bands, the usual signatures of a volatile, rich body warming under solar radiation. But then more objects were tracked, and something didn't add up. The relative intensity ratios between the CO2 and H2O emission lines were almost identical across multiple inbound objects. That level of uniformity is virtually unheard of in cometary physics. Typical comets display a wide spread in volatile composition, shaped by their individual formation environments. This group, however, exhibited matching volatile fractions down to decimal precision. It was as if they were copies or fragments of a single, tightly controlled chemical recipe. Beyond volatiles, infrared and UV spectra revealed broad absorption features consistent with complex organics. Long-chain carbon molecules not usually observed at such strength and purity. These spectral curves weren't diffuse or noisy. They were crisp, sharp, and highly structured, more like the engineered composites found in advanced material science than the messy signatures of primordial ices. Several laboratories flagged anomalous reflectance plateaus at 3.2 to 3.6 microns, a region associated with synthetic polymer analogues. But the most unsettling element wasn't chemical, it was temporal. Within hours of crossing the same heliocentric distance thresholds, multiple objects showed identical spectral evolution patterns. Surface temperatures climbed in lockstep, outgassing rates spiked on the same timeline, and the organic spectral peaks intensified together, suggesting simultaneous exposure or activation of internal layers. In natural objects, even those from a shared origin, this kind of synchronous behavior doesn't happen. They heat at different rates, they shed material unevenly. Yet here, 17 objects appear to be responding to the Sun as if governed by the same internal timing mechanism. The polarimetric signatures deepen the puzzle. Normally, light scattering from cometary dust creates noisy polarization curves. These bodies, however, displayed narrow, repeatable polarization transitions at specific phase angles nearly identical from one object to the next. A single polarization kink appearing at precisely 28 degrees emerged across the entire burst group. No random debris field behaves this cleanly. At this point, one explanation gained traction in the background, that these are not typical ERT objects at all, but compositional clones, either fragments of something larger that underwent controlled fragmentation, or bodies that share an engineered template. If these are natural, they're the most chemically uniform objects ever recorded inbound toward the Sun. If they're not, then the uniformity isn't coincidence, it's design. Still, public statements remained cautious. Official press briefings framed the observations as unusually tight clustering of volatile ratios, avoiding speculation. But behind closed doors, the spectroscopy lab shared raw data that revealed something more startling. When the infrared bands were run through Fourier analysis, weak harmonic oscillations were detected, oscillations repeating across multiple bodies. These aren't random noise signatures, they look like modulated spectral baselines, the kind sometimes used in low-power signal encoding. Skeptics suggested instrumental cross-contamination, but the signals persisted across different telescopes, instruments, and teams. Japan's Subaru telescope, Chile's VLT, and the Canary arrays all confirmed the same harmonic modulations. Even amateur infrared setups caught the tail end of the signature. The scientific community now faced an impossible choice. Either rewrite its models of how comets evolve, or consider the unthinkable possibility that these signatures are intentionally structured. The debate split rapidly. One camp proposed exotic but natural mechanisms, synchronized sublimation fronts triggered by a shared heliocentric trigger, possibly linked to a dust shell around 3I Atlas. Another pointed out that this level of chemical and temporal precision has no precedent in the solar system, and the longer the spectra were observed, the more the uniformity held. No drift, no deviation, as if the objects were tuned to the same threshold. The data are now pointing to something bigger than chance or clustering, something systematic, something controlled. But chemistry is only the beginning. The real shock came when astronomers began mapping the orbits themselves. When the orbits were first plotted, the results looked like static on a screen. The 17 inbound bodies weren't streaming in along a shared corridor, as one might expect from a common fragmentation source. Instead, they formed a chaotic-looking cloud of widely scattered orbital elements, inclinations ranging from near the ecliptic to steep, almost retrograde angles. Eccentricities varied from elongated elliptical tracks to hyperbolic escape trajectories. At first, this appeared to contradict everything implied by the synchronized timing and spectral fingerprints. If these bodies share a hidden logic, why are their paths so scattered? But the deeper the analysis went, the stranger it became. That scatter wasn't random. When projected not in heliocentric coordinates, but in rotating barycentric frames aligned with 3I Atlas's trajectory, a pattern emerged. All 17 orbits passed through a narrow phase-space corridor at different approach angles, but intersecting the same temporal node, a point in space and time less than 3 million kilometers from 3I Atlas's perihelion path. This is not how Oort cloud debris behaves. Normally, orbits disperse over time, never converging so cleanly on a single node. Orbital dynamicists at multiple observatories began running backward integrations. They expected to find a shared origin point far beyond Neptune, maybe a disrupted parent body or a common gravitational nudging event. Instead, the models produced nothing stable. The orbits don't trace back to a single source. In fact, many of them don't intersect at all in the past. Their trajectories diverge into deep space, separated by vast angles. Statistically, the probability that such a dispersed set of orbits would just happen to reconverge at the same temporal node is effectively zero. One team at the Paris Observatory described it bluntly. It looks less like they came from one place, and more like they were sent to one place. The orbital scatter itself contains clues. The angular momentum vectors are arranged in what appears to be a shell pattern around the perihelion corridor of 3I Atlas. If these were fragments, we'd expect velocity vectors to fan outward from a central breakup. Instead, they seem oriented inward, as if drawn or guided to converge from multiple directions toward a moving gravitational focus. This is where gravitational modelling hit a wall. The Sun's influence alone can't bend these paths into such tight temporal alignment. Perturbations from the major planets don't explain it either. Their influence would smear arrival times, not sharpen them. Some researchers began testing whether the gravitational field of 3I Atlas itself, if anomalously high, could act as a shepherding force. For that to work, however, the object would need to exert a gravitational influence orders of magnitude higher than its estimated mass. That's not a rounding error. That's an entirely new physical behaviour. Another theory emerged. Perhaps we're witnessing a form of coordinated orbital injection, a process where objects are manoeuvred independently along scattered paths but programmed to intersect a shared spatial point at a synchronized time. This concept is familiar in aerospace engineering, where satellite constellations are launched along staggered trajectories but meet in precise orbital shells. It is not something ever observed in natural cometary dynamics. Critics offered counterpoints. Perhaps these are natural resonances triggered by a galactic tide or a passing dark object, nudging many Oort bodies simultaneously. But even then, the result would not produce such surgical precision in convergence. Natural systems have noise. This event doesn't. One of the sharpest clues lies in their mean anomaly alignment. When plotted across the set, the anomalies fall within a remarkably narrow 0.7 degree window. That number alone is beyond coincidence. This isn't just a burst, it's choreography. Multiple agencies have quietly begun to classify the phenomenon less as an astronomical curiosity and more as a navigational enigma. 17 objects scattered across interstellar approach vectors, bending toward one narrow corridor around 3I Atlas. No known model can replicate this without invoking external control or physics, we don't yet understand. But orbital behaviour isn't the only synchronized layer in this story. As the objects draw closer to the Sun, their internal and external dynamics are beginning to move together like instruments in an orchestra. For weeks, astronomers had treated the burst as a statistical outlier, a spike in detections, a puzzle of trajectories, an unexplained cluster of spectral signatures. But then something happened that forced even the most cautious observers to rethink their frameworks entirely. As the inbound objects crossed the 1.2 astronomical unit mark, their behaviours began to synchronize in real time. 17 bodies separated by millions of kilometres started spinning, outgassing, brightening and modulating their thermal emissions with uncanny temporal precision. At first it looked like coincidence, then it became a pattern, and then it became impossible to ignore. The first indication came from light curve monitoring. Independent observatories across multiple continents, Chile, Japan, the Canary Islands and Australia, recorded brightness fluctuations that matched down to the hour. A single spike in reflected light would occur in one object, followed almost immediately by the same spike in another, then another, until the entire set of tracked bodies had echoed the same fluctuation within a 6-hour window. It wasn't a slow drift or a generalized brightening. It was a clean, repeated pattern, as if the objects were responding to the same internal clock or external cue. Statistical analyses of these synchronized fluctuations show a cross-correlation exceeding 0.96, a level of coherence never observed in natural cometary behavior. Then came the spin rate data. High-resolution radar imaging and photometric spin analyses revealed that their rotational periods were converging over time, tightening from an initial spread of nearly 5 hours to a narrow cluster between 8.7 and 9.1 hours. Even more unsettling, they weren't just converging, they were phase-locking, turning in step with each other like clockwork mechanisms. Natural objects don't do this. Even gravitationally bound systems like asteroid binaries maintain chaotic spin interactions due to tidal effects and irregular mass distributions. But these 17 inbound objects, widely separated in space, somehow found a shared rhythm and locked into it. The thermal maps added yet another layer. Infrared spectroscopy showed that their internal temperature gradients rose in parallel waves, each displaying a distinct dual-band warming cycle, an inner core spike followed by a delayed surface ramp-up. The lag between these phases was identical to the minute. This kind of precise temporal structure can't be generated by random solar heating alone. Normally, comets respond to solar flux based on surface porosity, spin orientation, albedo, and volatile content, producing chaotic, asynchronous temperature profiles. Here, the pattern was synchronized as if following a set of pre-calculated instructions. And then there was the most delicate signal of all, subtle trajectory nudges detected through long baseline interferometry. Over a span of just 3 nights, each object executed minuscule but measurable course adjustments on the order of centimeters per second in near-perfect temporal alignment. The changes were too clean to be explained by stochastic outgassing. They occurred at matched heliocentric distances, with vector orientations that appeared coordinated rather than random. To mimic such precision naturally would require an improbable combination of identical volatile distribution, spin axis orientation, and surface morphology across all objects, and as the data piled up, that probability collapsed to effectively 0. The most skeptical scientists tried to find mundane explanations, instrumental correlation errors, shared solar wind shocks, even unmodelled heliospheric particle flows, but those fall apart under scrutiny. The timing precision is too sharp. The synchronization persists even when accounting for differential solar wind pressures, radiation torque, and measurement uncertainties. This isn't a coincidence in heating, nor a shared environmental push. It looks more like a networked system, dispersed but coordinated. Behind closed doors, analysts started to use a new term, formation behavior. The phrase, borrowed from aerospace engineering, describes how multiple spacecraft maintain relative positioning and timing through networked control. This is the language of active systems, not passive debris. No known comet group, asteroid family, or meteor stream has ever demonstrated this kind of dynamic alignment. The synchronization isn't accidental, it is deliberate, or governed by a principle we don't yet understand. And the deeper this synchronization went, the more unsettling the implications became. If these objects can align their behaviors across millions of kilometers, they either respond to a shared external driver or possess some kind of internal coordination that functions far beyond current celestial models. That idea alone would have been enough to fracture long-held assumptions. But the next layer didn't just challenge models, it shattered them. Because when the thermal maps were pushed beyond surface readings and into fine-scale infrared differentials, astronomers started seeing patterns, shapes, structures, geometries that no natural comet nucleus should ever display. The thermal data was supposed to provide clarity. For decades, infrared mapping has been one of astronomy's most reliable tools for distinguishing between icy nuclei, rocky cores, and complex outgassing envelopes. Natural objects tend to produce messy, inconsistent thermal signatures, chaotic gradients shaped by spin, sunlight, and internal porosity. But when the incoming swarm around 3I Atlas reached the inner heliosphere, their infrared signatures did something no comet should ever do. They organized themselves into structured thermal architectures. The first real shock came from the deep-scan thermal maps generated by the Atacama Infrared Array in Chile. Analysts expected irregular heat distributions smeared across the surfaces of these objects. Instead, the thermal topography resolved into symmetrical lattice-like patterns, evenly spaced heat nodes across multiple bodies, repeating at proportional scales. The same spacing, the same pattern, the same thermal rhythm, replicated across 17 separate objects. Imagine scanning a snowball and discovering a perfect hexagonal grid glowing beneath its surface. That's the level of regularity being recorded. Within hours, other observatories confirmed the same phenomenon. Japan's infrared interferometry network reported synchronized dual band emissions, with energy spikes at identical intervals between core and surface layers. Normally, comet interiors heat unevenly, creating blotchy temperature gradients with unpredictable hotspots. Here, the heating looked engineered. Core temperatures climbed sharply, then stabilized at precisely 278 Kelvin before surface temperatures followed, delayed by the exact same temporal offset across all 17 objects. This is not stochastic behavior. It resembles a controlled thermal regulation system. More unsettling still were the internal geometries inferred from those temperature distributions. When scientists applied inversion models to reconstruct likely subsurface structures, they didn't get amorphous cores. They got repeating shapes, ring-like cavities, layered shells, and axial channels oriented consistently along each object's spin axis. 17 bodies, scattered across the solar system, each presenting identical thermal geometry. These aren't the chaotic structures of primordial ice. They are patterns that imply purpose, precision, and some form of design. Skeptics initially argued that the pattern might be a coincidence of observation angle, that perhaps the grid-like structure was a projection artifact caused by limited resolution. But this argument didn't survive the next wave of measurements. Multi-angle scans, including thermal phase curves taken during rotation, showed that the patterns remained stable regardless of perspective. As each object turned, the heat grid rotated with it like a rigid internal framework. There was no smearing, no deformation. It was real. Then came the harmonic fluctuations. Hidden beneath the static thermal gradient, analysts detected faint oscillations, small, rhythmic variations in emitted infrared energy. They repeated in cycles of exactly 1,800 seconds, every object, every rotation, identical periodicity. When those oscillations were overlaid across all 17 signals, they fell into perfect temporal alignment, like synchronized pulses from a network of machines. The implications were explosive. In natural bodies, heat dissipation follows simple thermodynamics. It never arranges itself into synchronized harmonic pulses across independent objects. That kind of precision demands either a shared external forcing mechanism, something influencing them all simultaneously, or internally regulated thermal systems. Either answer defies conventional cometary physics. A handful of theorists tried to stretch natural explanations to fit. Perhaps a passing gravitational wave was modulating internal pressures. Maybe resonant heating caused by synchronized spin resonances. Others whispered a more radical hypothesis, that these objects are not merely reacting to solar heating, but using it, converting it, storing it, or redistributing it according to some hidden structural logic. In other words, they behave less like dirty snowballs and more like thermal machines. The global response intensified. infrared assets normally reserved for planetary defense tracking were redirected toward the swarm. The European infrared network went to full alert status. Data sharing restrictions tightened. Official public channels downplayed the anomaly, calling it unusual thermophysical behavior requiring further study. But internally, the tone was different. There was no denying what the instruments were seeing. This was no noise artifact. This was structure. And structure means information. But thermal patterns were only the beginning of that revelation. Because once the temperature oscillations were isolated and analysed in the frequency domain, something else began to emerge. Signals. Faint, structured, multiband electromagnetic activity that seemed to mirror the rhythm of the thermal pulses. And when the spectrum was expanded beyond infrared, the picture grew darker, sharper, and far more intentional. At first, the signals were faint, background noise easily dismissed by anyone not looking closely. But the timing was suspicious. The structured thermal oscillations recorded in the infrared began to mirror faint electromagnetic activity in neighbouring frequency bands. It wasn't a gradual build-up, it was clean, crisp, and synchronized. Within 48 hours, what had looked like static transformed into something uncomfortably precise. A coordinated web of multiband transmissions spanning multiple wavelengths, emitted by 17 separate objects converging toward 3I Atlas's orbital corridor. The breakthrough came when analysts at the European Deep Space Network filtered the incoming radio noise against the harmonic frequencies detected in the thermal pulses. Suddenly, the noise collapsed into structure. Weak but unmistakable repeating carrier frequencies emerged, locked in step with the infrared pulse intervals. At 1,800 second cycles, the swarm of objects began emitting narrowband spikes across a spectrum ranging from low-frequency radio to high UHF. Individually, each signal was barely distinguishable from the cosmic background. But when the data from all 17 objects were phase-aligned, a network pattern appeared, like nodes in a mesh relaying packets of energy or information across vast distances. Further analysis revealed another unnerving layer. These emissions weren't isotropic. They weren't radiating in every direction like natural thermal emissions. They were directional, tightly focused beams aimed not randomly but toward each other. Each object was transmitting along a vector that corresponded to another member of the swarm, creating a geometrically closed communication lattice. The network wasn't just broadcasting, it was talking to itself. The signals themselves were not modulated in any conventional human protocol, but they displayed unmistakable hallmarks of structured information. Power fluctuations were discrete, not continuous. Phase shifts occurred at regular intervals, and the spectrum carried repeating sequences with a high degree of internal symmetry. Mathematicians brought in to analyse the signals applied entropy measures and found levels far below thermal noise. Whatever these objects were transmitting, it wasn't random. For days, agencies tried to find a natural explanation. Could it be plasma interactions, solar wind shocks, magnetospheric resonance? But those mechanisms are diffuse, chaotic, and smeared across broad timescales. These signals were sharp. They began and ended with precision. They rose and fell in harmonic lockstep with thermal pulses measured to the second. No solar wind model comes remotely close to reproducing this pattern. By the end of the week, the multiband structure was mapped in detail. Low frequencies appeared to carry broad envelope modulations, while the higher frequencies exhibited tight, repeating substructures reminiscent of handshakes or synchronization packets. One researcher described it bluntly during a closed technical briefing. It's not just a signal, it's a protocol. Even more chilling was the network topology that emerged when analysts plotted the transmission vectors. The 17 objects weren't communicating in a random mesh. They were arranged in a stable geometric configuration, locking into repeating triangular and hexagonal routing patterns. As the objects approached the Sun, the network flexed but didn't break. It adjusted dynamically, rerouting beams as if maintaining system coherence in real time. Such behaviour is completely alien to any known cometary or plasma structure. Observers noted something else, a faint secondary emission coming not from the individual nodes but from the empty space between them. It was as if the overlapping beams were creating interference regions, or something was happening inside the web itself. Those regions exhibited weak gravitational lensing effects, measurable only through ultra-precise VLBI baselines. It wasn't strong enough to resemble a large mass, but enough to register. Something in the space between the objects was bending light ever so slightly, like a structure forming out of nothing but alignment. Publicly, none of this was acknowledged. Official communiqué described the anomaly as unusual radio reflections from dust tails, but inside research networks, private channels were overflowing with encrypted telemetry, urgent video calls, and desperate attempts to keep pace with the data. For some, the signals represented the first compelling evidence that these objects are not inert at all. They are active, coordinated, perhaps even part of a single distributed system. The reality now facing astronomers was stark. Either an unknown astrophysical phenomenon is creating a perfectly synchronized communication lattice across millions of kilometers, or something is deliberately doing it. And if the signals are coherent and directional, then they're not simply a side effect, they are a function. But that function was about to reveal another, even stranger layer, because when instruments began detecting charged particle streams and plasma fields threading between the objects, it became clear that these weren't just signals travelling through space, they were building a physical network. The moment the electromagnetic signals began forming a recognisable lattice, attention turned to the space between the objects. If the transmissions were structured, analysts reasoned, they might be accompanied by plasma interactions, not unlike how the solar wind flows along magnetic field lines. At first, this seemed far-fetched. The distances between the bodies were too large, and interplanetary plasma densities too low for stable connections to form naturally. But then came the data from the solar observatories operating near the L1 point, and suddenly, what had been a hypothesis became a verifiable, physical structure in space. The first detections were subtle, faint fluctuations in local interplanetary magnetic field lines synchronized with the radio pulses already mapped between the objects. These fluctuations weren't chaotic swirls or solar wind turbulence, but they were coherent filaments, forming along vectors that matched the previously charted signal beams. Over the course of a single day, multiple solar probes, including those from the European Solar Orbiter Array and independent magnetometer networks, began registering sharp, synchronized deviations in field strength every 1,800 seconds. The periodicity was exact. No solar event on record has ever produced such precision. As analysts zoomed in on the signal, they found that the filaments were carrying streams of charged particles, predominantly protons and heavier ions, arranged in rhythmic bursts. What startled the research teams wasn't their existence. Plasma filaments are common in space, but their stability. These streams held shape for hours, threading between objects separated by millions of kilometers without dispersing in the solar wind. It was as if something was guiding and maintaining the current, creating stable corridors of magnetized plasma. When visualized as a dynamic network model, the formation resembled a massive, slowly rotating web. Not static, but adaptive, reconfiguring as the objects shifted positions. Some filaments thickened, others dimmed, but the geometry of the network held, anchored by the relative positions of the 17 objects. The plasma links appeared to reinforce the electromagnetic transmissions, creating a dual-layer structure, information travelling across tightly focused radio beams, and energy or charge moving through magnetic filaments. The plasma's behaviour violated expectations. Normally, charge particle flows this long should collapse under diffusion and irregular solar pressure. Instead, these filaments tightened, sharpening their boundaries as the objects drew closer to perihelion. Measurements showed confinement levels orders of magnitude higher than the surrounding solar plasma. Some segments even exhibited negative differential resistance, a trait rarely seen outside controlled laboratory conditions. The field geometry suggested that the objects were stabilizing the links actively, whether through internal processes or some as yet unknown physical mechanism. When scientists overlay the timing of the plasma surges against the 1,800-second signal pulse, they matched perfectly. Every electromagnetic burst was followed by a surge in particle flow along the corresponding magnetic filaments. This wasn't a random interaction. It was a coordinated energy transfer event, happening in perfect rhythm across 17 separate nodes. One of the most striking observations came from interferometric imaging, which captured faint glow regions where the filaments intersected. These junctions weren't attached to any object. They existed in open space, sustained purely by the overlapping fields. Inside those junctions, magnetic intensity spiked dramatically, as if multiple streams were converging to form temporary localized hubs, points of high energy density. The geometry mirrored the underlying transmission lattice mapped earlier, a web of triangular and hexagonal formations, now with glowing plasma threads visibly connecting them. Publicly, none of this was released. The official explanation remained highly unusual solar wind interactions with cometary ion tails. But the data told a different story. These weren't passive tails being swept by the wind. They were structural conduits, behaving more like the backbone of a system than the byproduct of natural heating. Privately, plasma physicists began to use language they'd never expected to apply to a natural celestial phenomenon. Waveguides, coherence, stabilized current sheets. A few even went further, whispering what others were afraid to say out loud, that the swarm was behaving less like a collection of inert rocks and more like a distributed machine, one that was activating its own infrastructure as it approached the sun. But the magnetic web was only part of the anomaly, because while the network tightened, another signal began to emerge, one far more subtle and far more difficult to explain away. Observatories started picking up slight distortions in the way background starlight bent as it passed through the regions between the objects. These weren't magnetic or electromagnetic signatures, they were gravitational. For weeks, the strange electromagnetic and plasma behavior of the inbound swarm had pushed comet science into uncharted territory, but gravity, unlike radiation, unlike plasma, was supposed to be stable, predictable. It is the quiet background fabric through which everything else moves. So when multiple observatories began reporting measurable gravitational anomalies in the regions between the objects, the tone of the scientific discussion changed from cautious curiosity to stunned silence. Gravity isn't supposed to behave this way. The first evidence came not from optical telescopes, but from stellar occultation tracking, precise measurements of how background starlight bends as it passes behind massive bodies. Normally, small cometary nuclei exert no detectable gravitational lensing at all. Their masses are simply too insignificant. Yet in early October, a faint but consistent micro-lensing effect was detected in the empty space between several swarm members. Light wasn't bending around the objects themselves, it was bending through the plasma junctions formed where electromagnetic filaments crossed. The distortion was weak but unmistakable. Something was accumulating mass, or something that behaved like mass, in the void between the objects. Initially, this was dismissed as an instrumentation error, but the signal didn't go away. In fact, over the next several days, the microlensing effect strengthened, tracked independently by the Very Large Telescope in Chile, the VLBI Radio Interferometry Network, and Japan's Hypersuprime Deep Survey Array. All three systems, operating at different wavelengths and using different methods, converged on the same conclusion. Gravitational lensing was occurring in places where there should be nothing. The inferred equivalent mass of these invisible nodes grew from negligible to comparable to a small asteroid, and then beyond. The anomalies had a pulse, every 1,800 seconds, the same rhythm already established in the electromagnetic and plasma networks. The gravitational signal intensified slightly before settling back down. The effect wasn't random or drifting, it was phased, synchronized to the larger system. For a long time, gravitational lensing was considered a passive consequence of mass, not something that could oscillate on a timed interval. But what the instruments were registering was something that behaved as if gravity itself was being modulated. By the second week of observations, the gravitational signal had evolved beyond mere microlensing. Tiny but measurable deviations in the predicted trajectories of some swarm members were observed. They weren't being pulled off course by external bodies like planets or the sun. Instead, they appeared to be subtly responding to gravitational wells forming inside their own network. It was as if the web they had woven was starting to generate its own collective gravity, binding the swarm more tightly together. The precision of this gravitational choreography was staggering. Each node's field rose and fell in perfect sync with the thermal pulses, the electromagnetic spikes, and the plasma flows. There was no lag, no drift, no desynchronization, and as the swarm approached perihelion, the gravitational strength of these nodes increased at an accelerating rate. Simulations showed that if the trend continued, the collective gravitational influence of the swarm could temporarily rival that of a mid-sized moon, even though the physical mass of the objects themselves was far too small to account for it. This discrepancy isn't a rounding error, it's a break in the model. Several teams tried to salvage classical physics. Maybe the plasma filaments were concentrating solar wind particles in ways that mimicked extra mass. Maybe measurement noise was being amplified through data stacking. But those explanations collapsed under independent verification. The signals were too clean, too synchronized, too persistent. What was happening in those junctions should not be possible under Newtonian or even relativistic expectations. This is where theoretical physics began to step in. Some suggested the plasma and electromagnetic structures might be modifying space-time geometry locally, perhaps through a yet undetected coupling between electromagnetism and gravity. Others proposed that the swarm was exploiting resonant gravitational modes, something akin to collective field behavior seen in condensed matter systems, but scaled to astronomical distances. And a smaller, quieter group began to use a phrase that, until now, had belonged more to speculation than to observational astronomy: emergent gravity. If gravity is being generated or amplified through the network, then the swarm isn't just moving through space, it's reshaping it. That realization sent ripples far beyond astronomy departments. Defense agencies, space agencies, and research consortiums began closing ranks, restricting telemetry flows, pushing some observations behind classified channels, and just as the gravitational signals seemed to stabilize, something even stranger began to emerge at the quantum scale. Small but statistically significant correlated fluctuations in distant instruments, as if the gravitational nodes were influencing systems far beyond their immediate region. The gravitational anomalies should have been the final limit, microlensing in empty space, oscillating fields behaving like mass, synchronized with thermal and electromagnetic pulses. Those alone were enough to stretch existing models to their breaking point. But what happened next pushed the discussion beyond astrophysics entirely, into the domain of fundamental physics itself. By mid-October, as the swarm tightened its network and its gravitational web deepened, researchers began to notice anomalies far from the objects themselves. Delicate, correlated fluctuations appearing in instruments thousands of kilometers away. Something was reaching out. Something invisible was rippling through the fabric beneath everything. It began at the Hanford Interferometry Station, one of the world's most sensitive gravitational wave observatories. The facility recorded a series of faint repeating phase deviations every 1,800 seconds, perfectly synchronized with the swarm's internal rhythm. Initially, the readings were dismissed as background noise or low-level seismic interference, but over the following days, similar anomalies appeared at the Virgo site in Italy, then at Kagra in Japan, and finally, in a pattern that could no longer be explained away, at multiple precision timing facilities across the globe. These weren't strong signals, they were subtle, fluctuations so small they skirted the edge of detectability. But they were coherent, they rose and fell together, and they mirrored the swarm's heartbeat like a distant echo. What stunned the physics community wasn't just the synchronization but the spatial range of the effect. The fluctuations appeared simultaneously on instruments separated by continents, registering within the same pulse interval, deviating from expected background noise in a way that implied a global-scale field coherence. In essence, something happening around the swarm was reverberating across space-time, faintly but measurably, with a level of precision that existing gravitational models cannot explain. No known natural event, not solar flares, not seismic activity, not cosmic rays, matches the timing signature. A second wave of evidence came from atomic clock networks, those used to synchronize deep space navigation and high-energy experiments. Around the same time the gravitational echoes were detected, ultra-stable clock arrays began to drift in subtle, identical patterns. Their phase noise increased in rhythm with the 1,800-second pulse, and, most importantly, that the drift was correlated, not random. In normal circumstances, noise between distant clocks is uncorrelated and averages out. Here it moved like a tide, synchronized, global, and centered on the exact period traced by the swarm. Quantum physicists were forced to confront a possibility they had long avoided outside of theoretical papers, that the gravitational anomalies were entangled with non-local effects. The idea that multiple distant points could exhibit coordinated quantum-level fluctuations without direct interaction has long been discussed in the abstract, but never measured on a planetary scale. Yet here the synchronization wasn't speculative. It was logged, repeated, confirmed. There were two major interpretations. The first, cautious and technical, suggested that the swarm might be inducing coherent spacetime oscillations, a kind of resonant standing wave generated by its plasma gravity lattice, rippling outward across the heliosphere. The second interpretation was less comfortable, that the swarm was using those oscillations deliberately, the 1,800-second rhythm now threaded through every layer of observation. Thermal, electromagnetic, plasma, gravitational, and quantum. The deeper scientists looked, the more it appeared that these objects weren't just responding to the environment, they were shaping it with precision. Attempts to model the echoes revealed a chilling pattern. The amplitude of the quantum fluctuations wasn't constant. It was growing, slowly, steadily with each passing day. The swarm's gravitational lattice seemed to be pulling more of spacetime into its synchronized envelope, expanding its reach far beyond its physical footprint. No one could explain how. But every observatory that pointed a sensor, no matter how far away, was now seeing the same rhythm. This convergence, the stacking of anomalies across every measurable domain, marked a point of no return in the scientific debate. Skepticism began to crack. Theoretical papers moved from if to how. A few dared to ask the question aloud: if these are not natural objects, then what kind of system can synchronize the fabric of reality itself across millions of kilometers? And why now, in the narrow window around 3I Atlas's perihelion? The echo was no longer confined to telescopes. It was bleeding into our measurements of space and time, and whatever was happening, it was accelerating. By the time the quantum echoes were confirmed across global sensor networks, the anomaly had crossed an invisible threshold. It was no longer a subject of academic debate, a strange astronomical curiosity to be quietly observed from the margins. It had become something else entirely, a planetary priority. The synchronized rhythm of 17 objects orbiting in concert with 3I Atlas had forced every major observatory, agency, and scientific institution on Earth into a coordinated state of alert unlike anything seen before in modern science. The first to react weren't governments. They were the independent observers, university telescopes, private interferometry arrays, and amateur astronomers who had been quietly following the strange pattern weeks before it became public. Their scattered data streams, usually fragmented and niche, began converging into something bigger, an informal global network. They tracked the synchronized light curves, the electromagnetic pulse intervals, and the growing gravitational distortions. Some of them even caught early signs of the plasma filaments. It was this loose grassroots coalition that noticed the 1,800-second pulse was reverberating globally. They were the first to ring alarm bells in professional circles, and within hours those circles began to mobilize. When the signal reached the large instruments, everything accelerated. Major ground-based arrays were retasked overnight. Telescopes that normally required months of advanced scheduling were suddenly made available in emergency time blocks. The European Southern Observatory reoriented entire segments of its network toward the swarm corridor. The deep infrared arrays at Mauna Kea went into continuous scan mode. And the radio interferometry lines, the same ones once used to map black hole shadows and pulsar signatures, began monitoring the harmonic emissions threading between the swarm members with precision never before applied to cometary objects. What had been a quiet observation campaign now became a coordinated planetary watch, running 24 hours a day. Then came the governments. Within a week, space agencies and military networks had quietly fused their telemetry infrastructures into a single shared observation grid. The European Space Agency initiated daily classified briefings with NASA, JAXA, and Roscosmos. Communication satellites at geostationary altitude were retasked for passive data interception. Deep space tracking assets previously pointed toward Mars missions and asteroid monitoring were redirected toward the inbound swarm. What made this response different wasn't just its speed, it was its breadth. This wasn't a single trajectory problem like an asteroid threat. It was a distributed system, one with multiple unknowns and rapidly increasing complexity. Behind the scenes, information control protocols were triggered almost immediately. Public channels spoke of unusual cometary behavior, framing the situation as a scientific curiosity, nothing more. But inside closed briefings, the language changed. The synchronized electromagnetic emissions, the expanding gravitational field, and the quantum scale echoes were described not as anomalies but as signals. structured, intentional, persistent. Monitoring frequencies across the spectrum, from LF radio to microwave, was tightened. Amateur signal logs that began circulating online were flagged and removed. Even academic researchers found themselves asked to sign revised non-disclosure agreements to retain telescope access. The scientific community itself was split down the middle. On one side were those who insisted on treating the phenomenon within existing physical frameworks, however strained they might be. On the other were those who quietly admitted that no known model could hold this many synchronized layers together. Astrophysicists found themselves sitting in the same rooms as defense analysts, quantum theorists, and orbital mechanics specialists, all struggling to make sense of what they were watching unfold. Every 1,800 seconds, their instruments pulsed in time, with something millions of kilometers away. Every 1,800 seconds, the swarm spoke, not to them, but to itself. The infrastructure supporting the response was staggering. Supercomputers at CERN, the NASA Ames Research Center, and Germany's DSY Institute were linked into a continuous data stream. These machines weren't just processing orbital elements. They were running real-time adaptive models to predict how the network's plasma structure, gravity nodes, and signal web might evolve as the swarm approached perihelion. At first, the models assumed linear growth, but after several cycles, they had to be reconfigured. The system wasn't linear at all. It was accelerating, folding new energy into itself, amplifying its own signal with every pulse. By the third week of October, the response shifted from passive observation to strategic coordination. High-orbit assets were repositioned. Low-thrust reconnaissance probes near Earth's Lagrange points began drifting toward more advantageous angles for interception. Specialized sensors on solar observation satellites were recalibrated to catch the pulse before it vanished behind the sun. Emergency data agreements were signed between agencies that hadn't collaborated in decades. The entire structure of Earth's deep space monitoring infrastructure began bending around a single event. Inside secure briefings, a sharp divide formed. One faction argued for complete transparency, to treat the anomaly as a global scientific moment, to publish everything in real time. Another faction, backed by state agencies, advocated for tight containment until more was understood. They feared chaos, panic, or geopolitical destabilization. And overshadowing both sides was a third, quieter concern. If the swarm's behavior was deliberate, then humanity wasn't merely observing a natural phenomenon. It was witnessing the actions of something capable of manipulating fields, energy, and gravity across astronomical distances. Something watching the same sun we do, but not as a star to orbit, as a point of convergence. For all the noise, secrecy, and analysis, one truth hung in the air of every control room and scientific conference hall. Earth had no control over what was unfolding. The swarm wasn't aimed at us. It wasn't broadcasting toward us. It wasn't even acknowledging our presence. It was simply following its pattern. Precise, accelerating, synchronized. Humanity could do nothing but watch, measure, and scramble to understand a language written in fields and forces, and then, as the perihelion date drew closer, a decision was made that would define the next stage of the response. Observation was no longer enough. For the first time in history, a mission would be rushed into deep space not to defend Earth, but to intercept a gravitational, electromagnetic, and quantum structure no one yet understood. It was risky, desperate, and unprecedented, but it was the only way to look directly into the swarm before it slipped behind the sun. In the history of spaceflight, no mission had ever been conceived, authorized, and prepared as quickly as this one. Intercept missions usually take years of design, engineering, and logistical coordination. This one was assembled in less than 3 weeks, not because the technology was ready, but because time was running out. Once the swarm and 3i Atlas passed behind the sun at the end of October, line-of-sight observations would collapse for weeks. And for an event of this scale, synchronized electromagnetic lattice, self-reinforcing gravity nodes, quantum field echoes, there would be no second chance. Either humanity moved now, or it watched the most significant cosmic anomaly in modern history vanish behind a wall of stellar radiation. The mission began with a series of encrypted briefings between the European Space Agency, NASA, and select private aerospace contractors with the capability to deploy a small probe on extremely short notice. Larger spacefaring nations contributed observational assets, but only one solution was realistic: launching something fast, small, and maneuverable, capable of reaching the swarm's electromagnetic perimeter before perihelion. No large launch vehicle could be prepped in time, but there were dormant assets in orbit. Small modular interceptors originally built for asteroid flyby studies, never deployed operationally. Their propulsion systems weren't designed for deep space chases, but with clever orbital mechanics, gravity assists, and a stripped-down payload, they could get close enough. What emerged from those briefings was something unofficially codenamed Project Veil. Its objective was simple in writing, impossible in execution: approach the outer edge of the swarm's plasma magnetic lattice, maintain sensor lock on its field behavior, and transmit continuous readings back to Earth before the solar occlusion window. The probe wouldn't aim for physical contact. That was deemed suicidal given the unknown field intensities. Instead, it would try to slip through the outer interference layer, mapping the structure from within. If successful, it would return humanity's first direct measurements of whatever force was holding the system together. The probe itself, hastily renamed Argus after the many-eyed sentinel of myth, was a skeletal craft, a titanium frame wrapped around high-gain antennas, an ultra-stable atomic clock array, a compact interferometry package, and a hardened plasma environment sensor suite. No crew, no return capacity, just a single burn trajectory and a network of automated telemetry streams. It would act as a flying instrument, designed to survive in the field for only a few hours, maybe days, but long enough to pierce the silence between Earth and the swarm. The engineering hurdles were brutal. The Argus platform had to launch on a tight orbital corridor that intersected the electromagnetic halo of the swarm at a narrow angle, avoiding both direct solar radiation and the growing gravitational envelope forming between the objects. The timing was unforgiving. Miss the burn window, and the probe would arrive too late, its trajectory locked out by the sun's position. On October 20th, final telemetry simulations projected a 38-hour intercept window, the only viable slot left before the swarm rotated out of reach. The launch was never televised. No announcements were made. It lifted quietly from a secure pad in French Guiana under the cover of a late-night launch manifest described as a high-energy trajectory test. Those who knew what was really leaving the ground understood the stakes. This was not an experiment. It was the closest thing to first contact reconnaissance humanity had ever attempted. In the days that followed, every deep space tracking station on Earth pointed toward Argus. The probe cut through interplanetary space at high velocity, its sensors already picking up the faint oscillations from the swarm as it approached. At first, the readings matched ground-based data: the 1,800-second electromagnetic pulse, the plasma filaments threading between nodes, the gravitational ripples. But as Argus crossed the 0.9 astronomical unit threshold, new data began to appear. Low-level electromagnetic fields not visible from Earth emerged, subtle background structures, carrier frequencies beneath the primary pulses, like faint whispers beneath a chant. The swarm wasn't broadcasting one signal, it was broadcasting many, layered and nested like an encryption protocol. Meanwhile, Earth's response infrastructure intensified. New intercept windows were plotted for ground-based arrays, radio telescopes were retuned to match Argus's real-time readings, and quantum timing labs linked their clocks to the probe's ultra-stable reference systems. Every new byte of telemetry confirmed what had already become clear: this was not a comet swarm in any conventional sense. No cluster of icy rocks or debris field could emit structured, layered, synchronized signals across multiple energy domains while maintaining gravitational coherence. Something was at work inside that network, something precise. The human cost of the operation was also real. Multiple agencies burned through emergency budgets, research access was locked down, and dozens of scientists found their work suddenly classified under new security clearances they hadn't even applied for. Civilian astronomers who had tracked the anomaly from the beginning were cut out of live feeds, replaced by carefully edited data packets. The public knew something was happening, but they had no idea how far things had escalated behind closed doors. As Argus neared the outer perimeter of the swarm, the signals became clearer, sharper. The probe's instruments recorded rising plasma densities, magnetic field coherence levels orders of magnitude above predictions, and gravitational distortions that made orbital mechanics simulators break down entirely. And then, with less than 12 hours before perihelion, Argus detected something unexpected, a pulse deviation. For the first time since the phenomenon began, the swarm's heartbeat shifted. The 1,800-second rhythm tightened to 1,620 seconds across all frequencies simultaneously. It was as if the network knew Argus was there. Inside control rooms around the world, the atmosphere shifted. What had been a cautious scientific mission was now a silent standoff between human instruments and something vast, intelligent, or operating under principles we didn't understand. The swarm was no longer just doing something, it was reacting. Argus continued its approach, transmitting every byte it could. And as the network's pulse began to accelerate, scientists realized the swarm's structure wasn't just stabilizing around 3 Atlas's perihelion. As Argus closed in on the outer perimeter of the swarm, the scientific framework holding the phenomenon inside the boundaries of existing physics began to fracture under its own weight. For weeks, teams around the world had tried to explain the synchronized behavior of the 17 objects in terms of cometary activity, plasma dynamics, or gravitational anomalies. But the data coming from the probe, raw, high-resolution, uninterpreted, didn't bend to theory. It broke it. The closer Argus got, the clearer the signal became. The swarm wasn't behaving like a set of objects bound by gravity. It was behaving like a system. The first model to fail was orbital mechanics. Standard N-body simulations assumed that each object's trajectory should be slightly perturbed by the collective gravitational nodes. But as Argus streamed telemetry through its stabilized interferometers, it revealed a reality far more complex. The swarm's orbital configuration was evolving in real time, adjusting its relative positions with surgical precision. Tiny corrections rippled across the network like signals through a nervous system. One object would adjust its course by millimeters per second, and seconds later, the others would respond in perfect counterbalance, preserving a geometry that didn't match any stable natural configuration. These weren't random perturbations, they were instructions being followed. The second failure came in thermodynamics. The probe's infrared sensors confirmed what ground arrays had only suspected. The swarm's heat patterns were not residual or chaotic. They were actively regulated, rising and falling in lockstep with the electromagnetic and gravitational cycles. In some segments, Argus detected negative thermal gradients, regions where heat seemed to flow inward instead of radiating outward. No known comet, asteroid, or plasma structure behaves this way. Something inside the swarm was absorbing energy, reorganizing it, and re-emitting it according to a precise schedule. It was the behavior of a closed-loop energy system, not a cluster of inert debris. Then the deepest foundation cracked, gravity itself. The gravitational field recorded inside the swarm's electromagnetic perimeter wasn't just stronger than predicted, it was structured. Instead of a smooth potential well, Argus's instruments recorded oscillating gravitational harmonics pulsing with the same 1,620-second rhythm that had replaced the earlier 1,800-second heartbeat. The swarm wasn't simply generating extra gravity, it was shaping it. The field rose and fell like a breathing lung, synchronized across millions of kilometers. For a handful of scientists listening to the live feed, that moment was catastrophic. This wasn't gravity as a passive consequence of mass. This was gravity as a controlled medium. The theoretical collapse spread fast. Plasma physicists, gravitational theorists, quantum field specialists, entire disciplines found themselves without tools to interpret what they were seeing. Some proposed exotic but still semi-natural explanations, coherent electromagnetic field structures coupling with spacetime fabric, perhaps amplifying fluctuations. Others whispered darker possibilities, direct manipulation of gravitational fields by an intelligence or mechanism operating at a scale beyond human engineering. Even conservative models now required new physics to make sense of the swarm's coherence. Behind closed doors, research centres began abandoning attempts to explain the swarm through conventional comet science. Internal memos spoke in stripped-down language, networked behaviour detected, real-time response confirmed, field coherence increasing. The tone was no longer speculative, It was diagnostic, as if describing the early stages of a known phenomenon, only no one had ever seen anything like it before. Argus, hurtling through the swarm's outer interference layer, recorded a sudden frequency bifurcation. The primary signal split into two layers, a low-frequency envelope modulating the gravitational pulse and a high-frequency carrier embedded within the electromagnetic lattice. This wasn't static, it wasn't random, it was structured with mathematical elegance, containing repeating prime intervals and non-integer harmonic ratios. Information theorists watching the stream began running entropy analyses in real time. The results came back unambiguous. This was a low-entropy structured signal, consistent with encoded data or command traffic. At this point, the theoretical debate effectively ended. No model rooted in natural cometary behavior could produce a structured hierarchical signal stack synchronized across thermal, electromagnetic, gravitational, and quantum layers. Even the most cautious agencies dropped the language of coincidence. Internally, the anomaly was no longer referred to as the swarm. It had a new designation, the Atlas Network. And with that redefinition came a quiet, sobering realization. If this was a network, then 3I Atlas wasn't simply a wandering body at the center of it. It was the anchor, or something even more central. The swarm's geometry, its pulse frequency, and its lattice structure all pivoted around its trajectory like planets around a star. The closer Argus drew, the more the probe's instruments revealed an organized interior pattern, a geometry hidden in the fields themselves. Theories collapsed, paradigms cracked, but something else began to take shape in their place. Not an explanation, but a recognition. Humanity wasn't observing debris or coincidence, it was watching a system come fully online. As Argus moved deeper into the swarm's perimeter, the narrative of what this event represented shifted irreversibly. For months, the scientific world had been struggling to fit the phenomena into the language of comet science, trying to reconcile plasma, gravity, and electromagnetic data with centuries-old frameworks. But now, with Argus feeding high-resolution, multi-layer telemetry directly from inside the network's edge, those frameworks collapsed under the weight of something that was never meant to fit inside them. What emerged in their place was not a single explanation, but the slow, inevitable birth of a new branch of physics, one built not on classical assumptions, but on what the Atlas network was demonstrating in real time. The first crack in the old structure was the behavior of spacetime itself. Gravitational lensing around the network no longer behaved like a smooth, passive curvature. Instead, it pulsed, shifted, and then folded into harmonic patterns. Observatories on Earth detected phase-aligned distortions across multiple light sources, like invisible ripples fanning outward from a controlled center. For the first time, space-time wasn't simply reacting to mass. It appeared to be coherently structured by a timed sequence, and the rhythm wasn't arbitrary. As Argus closed within 200,000 kilometers of the nearest plasma filament, the 1,620-second pulse split into secondary harmonics. 540 seconds, 270 seconds, 90 seconds. These were not chaotic fluctuations. They formed a perfect harmonic series, a cascade that suggested precise field control. Meanwhile, the probe's magnetometer array began detecting localized stable pockets of what could only be described as field confinement zones, regions where electromagnetic fields, plasma flows, and gravitational oscillations were braided together into self-stabilizing knots. These knots didn't disperse under solar wind pressure. They didn't fluctuate randomly. They remained coherent, as if locked into place by an underlying algorithm. No known natural process produces field configurations that persist under such dynamic conditions. The closest analogy in human technology would be artificial confinement systems, fusion fields, plasma rings, resonant cavities, but this was happening on a scale measured in millions of kilometers. The quantum echo networks detected earlier on Earth began intensifying as well. Subtle but measurable fluctuations in interferometers across the globe now showed phase entanglement between distant locations, not just between detectors, but between detectors and the probe itself. Argus's onboard quantum clock began drifting in perfect synchronization with Earth-based instruments, despite being separated by astronomical distances and under entirely different field conditions. To the astonishment of the physicists watching, it was as though the Atlas network had pulled Argus's internal quantum reference into a shared timing lattice, an invisible metronome keeping everything in sync. It was at this point that entire theoretical disciplines fractured and recombined overnight. Classical gravity couldn't explain what was happening. Quantum mechanics could describe parts of it, but failed to account for its macroscopic coherence. Plasma physics could outline the structure but not its impossible stability. The phenomenon didn't fit into any single domain because it was bridging them all. A new term began circulating in closed research circles: field convergence. It wasn't a theory yet, just a placeholder, a way to name the fact that electromagnetic, gravitational, thermal and quantum domains were operating here as a single unified system. And at the centre of that system, Argus's instruments recorded something even stranger. As it approached the first junction point, a place where multiple plasma filaments converged into a magnetic node, its gravimetric sensors spiked. But it wasn't mass that caused the reading, it was curvature without mass, a region where spacetime itself appeared to warp, independent of any detectable physical object. Light passing through it was delayed, bent fractionally, and then realigned with unnerving precision. The node behaved like a lens, but it wasn't bending light randomly. It was bending it with intent, focusing it into thin, invisible channels radiating deeper into the structure. This changed everything. If the Atlas network could sculpt spacetime itself, it meant that gravity was not the driving force behind its architecture. Gravity was a medium, shaped and tuned the way humans shape electromagnetic fields in a circuit. This wasn't simply a new astrophysical phenomenon, it was a demonstration. One that exposed the limits of human physics like a spotlight revealing the edges of a map too small for the territory it's meant to cover. The impact of these revelations rippled through scientific institutions in real time. Old rivalries between disciplines dissolved overnight as physicists, astronomers and engineers worked side by side, pulling apart Argus's live stream frame by frame. Teams at CERN, Caltech and the Max Planck Institute independently confirmed that the phase harmonics of the gravitational field matched mathematical structures predicted in certain speculative unification models previously dismissed as beautiful but impractical math. Now they weren't just theories, they were telemetry. But as staggering as the implications were, one realization hung in the air like a cold weight. If the Atlas network was controlling spacetime at this scale, it was doing so with precision far beyond anything humanity could replicate. This wasn't something that had just emerged, it was something built, something that operated with purpose, and that purpose, whatever it was about to reveal itself as perihelion approached. The pulse frequency was accelerating, the geometry was tightening, the field convergence was nearing its peak state. By the final week of October, everything was moving toward a single moment. The Atlas network's rhythm, once a distant anomaly, had become a planetary heartbeat, pulsing through every sensor system humanity possessed. The 1,620-second cycle that had replaced the earlier baseline was tightening further, shrinking with geometric precision. 1,440 seconds, then 1,260, then 1,080. It wasn't random drift, it was a countdown. Every reduction in pulse interval triggered a chain reaction through the electromagnetic lattice, plasma filaments, gravitational harmonics, and quantum echoes. It was as if the entire structure was converging toward a singular state. Observers began calling it what it clearly was, the signal horizon. Argus was already inside the outer perimeter by then, a silent, blinking node in the dark, hurtling through a gravitational environment unlike anything human technology had ever measured. Telemetry showed the plasma filaments tightening around the network, their densities increasing exponentially as perihelion approached. What had once been delicate thread-like currents were now thick bands of structured energy, glowing in wavelengths invisible to human eyes but blinding in the probe's sensors. Magnetic coherence reached levels that no simulation had predicted were even possible in open space, and within these filaments, gravitational pulses began aligning into a single, unified wavefront, a synchronized, system-wide surge that grew sharper with every passing hour. At mission control, there were no longer competing theories, only models trying to keep up. Teams that had once argued over explanations now spoke in short, precise fragments. Pulse contraction, field alignment, node stabilization. Everyone understood what the data implied, even if no one could fully articulate it. The Atlas network was preparing for a phase transition. Whether that meant an activation, a transmission, or something far stranger, No one could say. The structure of the lattice was no longer static, it was reconfiguring. Over just a few orbital cycles, the swarm's geometry shifted from its initial hexagonal web pattern into a tighter, nested formation, 17 bodies collapsing into a three-tiered spherical array around 3i Atlas. The plasma filaments, once connecting object to object, now began pulling inward, converging toward a central focal point somewhere inside the network. That point wasn't Atlas's nucleus. It was something deeper, embedded inside the geometry like the center of a resonant cavity. The gravitational harmonics registered by Argus revealed the scale of what was happening. Instead of scattered oscillations, the readings locked into a single dominant frequency, amplified exponentially by the tightening field. Light from background stars passing through the swarm's interior was bent in perfect symmetry, as though space itself was being shaped into a lens of impossible precision. The microlensing patterns weren't chaotic distortions anymore, they were engineered signatures stable to fractions of a microsecond. It was, in every measurable way, the behavior of an artificial system. The quantum echoes that had been whispering through Earth's interferometers became a roar. Distant labs from Hanford to Virgo to Kagra began reporting perfectly synchronized phase spikes across every instrument. Atomic clock drift wasn't just correlated now, it was identical. The entire planet was being drawn into a single phase lattice defined not by our machines, but by the Atlas network. Humanity's timing infrastructure, the same backbone used for GPS, navigation, communication, and physics experiments, was no longer operating independently. It was locked into someone else's clock. Inside mission control, the Argus telemetry feed became eerily regular. Every sensor spike arrived in clean intervals, every pulse built on the last folding the fields inward. Then, at T-minus 40 hours to perihelion, a new signal layer appeared, buried deep beneath the electromagnetic lattice. It wasn't a harmonic or a fluctuation or noise, it was a message. Not a message in any language, not a human pattern. It was mathematically exact, structured in prime intervals and non-integer ratios, the same architecture found in the swarm's physical design. At first, analysts thought it was a byproduct of the lattice itself, a resonance effect from the gravitational wavefront. But the structure was too deliberate. The ratios repeated in cycles, building larger patterns over time. Argus wasn't just listening to fields, it was listening to a transmission. The closer perihelion came, the clearer it became that this horizon, the point toward which the entire network was collapsing, wasn't merely a physical event, it was an information event. Something was preparing to broadcast, receive, or transform in a way humanity had never witnessed before. The gravity field, electromagnetic grid, quantum phase alignment. Every layer of the system was aligning toward a single pulse. One moment, all around the world, deep space monitoring stations fell silent. No one dared to speculate publicly anymore. Theories about extraterrestrial infrastructure, autonomous interstellar probes, or unknown physical phenomena hung in the air, unspoken but understood. Scientists weren't arguing about what the network was. They were bracing for what it was about to do. As Argus drifted closer, riding the edge of the magnetic filaments, its sensors began to register non-local field feedback. The probe's own transmissions were being folded into the lattice and reflected back at it, delayed by fractions of a microsecond, not from space, but from inside the field itself. The Atlas network wasn't just emitting a signal, it was listening. And then came the final confirmation. The pulse interval stabilized. Exactly 900 seconds. No drift, no jitter, no instability. Across every field, every frequency, every layer were a perfect phase lock. The signal horizon had been reached. The countdown was over. In that silence, every control room on Earth felt it, not as a sound, but as a weight. Something was about to happen. Something that would either rewrite our understanding of the cosmos, or reveal that it had never belonged to us at all. October 29th, 2025, perihelion. For weeks, everything had been moving toward this single second. Telescopes had followed the tightening geometry. Detectors around the world had synchronized to the pulse. Argus, small and fragile against the dark, had fallen silent except for the unbroken stream of numbers pouring back toward Earth. All signals now converged on a single beat. 900 seconds. The Atlas network was no longer changing. It was waiting. As the sun's corona flared in the background, the swarm structure locked into final formation. 17 objects, arranged in a configuration too exact to be natural, hovered in their orbital corridor like a frozen constellation. The plasma filaments had completed their inward collapse, braiding into a single glowing lattice that enclosed the core of the network. Within it, the gravitational harmonics reached peak amplitude, folding space-time like fabric drawn taut. For a brief moment, light itself seemed to hesitate when passing through the structure, bending, refracting, splitting into coherent interference patterns that didn't disperse. A gravitational lens had formed, but not around a mass, around a field. Back on Earth, the world held its breath. The signal was no longer faint. Every major interferometer, every deep space antenna, every high-orbit listening station was saturated. It wasn't noise. It wasn't random. The waveform was perfect, extending across the spectrum from sub-radio to soft X-ray, harmonized in a way no natural system could maintain. The last traces of uncertainty vanished. The Atlas network wasn't the product of blind physics. It was the manifestation of an architecture. Argus drifted closer, passing through the outer electromagnetic shell. The probe's instruments registered a drop in local entropy, as if the chaos of the solar wind itself was being suppressed inside the lattice. Plasma flows stilled, charged particle velocities snapped into narrow bands, magnetic field lines aligned into crystalline structures. Argus had entered the eye of the system, a zone where natural space seemed to stop behaving like space at all. Gravity, plasma, and light existed here, but on someone else's terms. Then it happened. At 1600 hours UTC, the pulse reached absolute coherence. The 900-second interval collapsed into a single monolithic spike, a burst that didn't just cross frequencies but fused them. Gravitational oscillations, electromagnetic harmonics, and quantum echoes struck together, folding into one pure structured wave. On Earth, sensors didn't receive it separately. They felt it everywhere at once. Like curves in unrelated stars flickered, interferometers lit up in perfect phase. GPS clocks jumped forward by an identical nanosecond. The entire planetary measurement framework flinched, not because of a shock wave, but because the baseline of reality had shifted. Argus's final transmission showed something no one was prepared to explain. As the spike propagated, the lattice didn't explode or disperse. It unfolded. The 17 objects vanished into a seamless, radiant geometry, a single, spherical field of structured light and gravitational curvature hanging behind the sun like an impossible mirror. Inside that geometry, the harmonic ratios that had defined the swarm's behaviour rearranged into a pattern far simpler than anyone expected. A series of prime intervals repeated, then inverted, then sent outward. It wasn't a language. It wasn't even information in the human sense. It was a signal of presence. The burst lasted exactly 900 seconds. Then, just as suddenly, it stopped. The plasma lattice collapsed back into emptiness. The gravitational harmonics evaporated. The quantum echoes fell silent. Telescopes searching the perihelion zone recorded only the brilliant glare of the sun and, scattered across its edges, the fading ion trails of 17 objects that were no longer there. Whatever the Atlas network had been, it was now gone. No debris, no traceable trajectory, just silence where something vast had existed a heartbeat before. But the effects remained. Timing systems across Earth were still phase-locked to an external reference that no longer existed. Quantum baselines had shifted subtly but permanently. The empty space where the swarm had formed retained a faint gravitational lensing signature, like the echo of something that had passed through but not entirely left. Whatever happened at perihelion wasn't just a transmission, it was a transition. In the weeks that followed, scientists argued, agencies denied, and the world tried to return to its ordinary rhythm. But instruments didn't forget. The echo embedded itself in the background noise of space, persistent and unyielding. Somewhere out beyond the glare of the sun, the harmonic structure was still pulsing, faint, distant, but real. The Atlas network had not appeared to communicate with us. It had not issued demands, sent messages, or even acknowledged our existence. It had simply used our star as a node, and then moved on. And as the final data packets from Argus were decoded, one fact settled in quietly across every lab, every briefing room, every sleepless observatory on the planet. We were never the audience. The signal wasn't for us. It never had been.